Hello Year 12 students, it's Mr. Mayor here doing a quick lesson for Year 12 Maths C on differential equations. The focus of this will be to solve the logistic equation, and this ties in or relates directly to task 2 of the assignment. So this lesson right now will focus mainly on that, but we'll also have a talk about two of the dominant models for population growth and the assumptions around those. So task 1 of the assignment, we've already looked at the exponential growth, okay? That's the Malthus model. So Malthus wrote an essay on population growth in the late 1700s, and he talked about the fact that unchecked population growth would be exponential, okay? So essentially no limit, just keep going. Obviously there would be a limit because at some point, resources would be used up, there wouldn't be much room left. There could be some catastrophe, some cataclysmic event that could obviously level a population, but with no other factors at bay, population growth would just go unchecked and exponentially grow. So this is task 1 of the assignment, by the way. Task 1, we had to solve this differential equation here, this DE, and if we look at it, we're saying the rate of population growth over time is directly proportional to the population at any time. So the greater the population, the greater the growth. Okay, and that's exponential. R is the rate of growth here. So we found in task 1, if we solve this differential equation here, we ended up with a function of this form, which is clearly just an exponential function. Okay, where p sub 0 is the initial population, and R is the rate. So they're the parameters, and that's very simple. But it's not sufficient in the sense that it doesn't factor in, things that could possibly sort of level off a population over time. Obviously, the planet the planet is not infinite. The resources on the planet are not infinite. So a population will find its limit at some point. Which brings us back to this thing here, the logistic equation, which is the Verhulst model, okay? So Malthus was exponential, right? He was proposing this idea back in the late 1700s. In the mid 1800s, Verhulst, a Belgian mathematician, he came up with the logistic model, this thing here. This again is a DE, differential equation. And basically what he said was this. He said that the rate of population growth was indeed proportional to the population at any time, but he also put in this mortality constant called mu, and he said that was, so he's saying that the decrease in the population based on this mortality constant was proportional to p squared. Okay, so what we find is when the population gets sufficiently large, it will start to level off, okay, based on this mortality constant. So this thing here, mortality constant. And we can think of the mortality constant as being a ratio of the rate of growth over k, which is the carrying capacity. Okay, so just a quick look at the logistic function. If we solve it, it looks something like that, an S-curve. Okay, so we can say this is population, this is time, and at the start, and this is the initial population, of course, at time 0, and we see at the start there is that exponential growth. Okay, but then at some point here, there's an inflection where the increase in population starts to turn the other way, and it heads towards this limit, this limiting value here, which we call K. Okay, now K is the carrying capacity for a population. So, and we can apply this differential equation to any population, not just human population growth. We could apply it to population growth in a country, or we could look at different species, bacteria, plants, whatever. And we could apply that even to brain tumours, okay? And we'll look at that example in a minute. So the carrying capacity is K, okay? So what we can do is we can then rewrite this as dp dt is equal to rp minus r over k p squared. And if we factorize that, we end up with rp outside of 1 minus p on k. And this is something like what you'll see on the task sheet, I think. So if I just have a quick squiz over now at the task sheet, I can see, yes, task 2, we have this exact equation here, which is labelled with an asterisk, and that's the one you have to solve. Okay, that's the one you have to solve. Now, one thing we can do just to simplify this a little bit more is to write it as dp dt equals rp. We can factorize the k out as well, or the 1 on k I should say. So we end up with k minus p. And this is probably the one that we'll work with, okay? So this is just a different version of that, which is in turn a different version of this. So the thing with Verhulst is he came up with this idea that population growth is proportional to the population at the time, but the decrease in the population would be proportional to the population squared. And so you can see this is adding to the population, but this is taken away from the population. So, and what we notice if we look at this S curve here, the logistic curve, is that the population will increase exponentially when p is small. Okay, so this is dominant here, but as p gets larger and we start to square it, then it really drops off. Okay, so good. All right, so let's get rid of that. That's just my initial waffle. The main focus will be algebraically, how do we solve this thing here? Okay, so here's essentially the theory around the logistic equation. Now, this one I've done with a different variable. So instead of using p, I'm using n. Okay, so n can refer to the number of in a population. So as we saw back here, this equation here that we came up with, the logistic equation, which is, well, it's a differential equation for the logistic equation. It's the same one as we've got here, and it's the same one that we've got here as well. So this one here is just using n in place of p. And we know the solution to this equation looks like this. Okay, so this is the explicit form of n equals some function of t, time. Okay, and the graph of this function looks exactly like this thing here. And we know that, it's asymptotic to the dotted line here, which is k, the carrying capacity. So carrying capacity. There we go. All right, so this solves to this. C is some constant, but through initial conditions we can figure out what C is, and C is related to the carrying capacity and the initial population. Now let me just check. I have a feeling, yes, I didn't think I had that right. So yeah, so C is actually K minus the initial population divided by the initial population. So we'll find that out as well. We'll figure that out at some point. Just quick chat about the variables at play here. N is a population, so that's this thing here. T is time. K, so parameters now. So K is the carrying capacity. So it's essentially the upper limit of the population. R is the rate of growth, and N sub 0 is the initial population. Right. Okay. So let's have a quick pause to come up with some jokes. So I'm just looking at one here. Why do mathematicians like parks? Because of all the natural logs. I know. Here's one that's worse. Did you hear about the statistician who drowned crossing a river? It was 3 feet on. Oh, stuffed it up. The river was three feet deep on average. Yeah. Okay. I'll stop doing jokes for now. Back to this. Okay, so how do we solve this? So let's start. So here's solving the DE, the differential equation, solving the DE asterisk. Okay, so here we go. All right, so dn dt, I'll just write it out again, is equal to Rn on k, and then k minus n. Now, the thing we've got to keep in mind here, because there's no numbers involved, it's all symbols. The thing we need to remember is that the variables are n and t, okay? So when we integrate, ultimately, we're going to be integrating, we need to make sure that the variables are the subject of our integration. In other words, they're the two variables. So, and it turns out that we can use separable equations here. So we can separate the variables. So we use that technique that we saw in class last lesson. So we can separate the variables, which means we can shove n. What that means is we put n on the left-hand side and we put t on the right-hand side, okay? So hopefully we can see already how that's going to happen here, right? So the n times k minus n, we'll shift that over to the left, so that's going to end up like this. So dn over n brackets k minus n. So now we've moved n to the left-hand side. On the right-hand side, we'll have whatever's left after we've cross-multiplied the n k minus n across, and that's going to be r over k, and then we move the t over, so that goes up, okay? So now we've done that. We've separated our variables, and know that n is a variable on the left, and we can see that n appears here and here, and then on the right we have t as a variable, okay? Now, we integrate both sides, so this is the technique for separable equations. Integrate both sides. So now I'm gonna cheat a bit here, because to integrate this thing here, it's not that straightforward. We actually have to apply partial fractions to allow ourselves to be able to integrate this thing here. Once we apply partial fractions, and I can come back and do that later, but once we apply partial fractions, this left-hand side here ends up looking like the integral of dn over n, and then plus the integral of dn over k minus n. And on top of that, we have 1 over k in brackets. Yeah, so this left-hand side, this thing here, becomes this thing here, okay? Now, obviously, we'll come back and we'll do that, but just for now, we just want to get to the solution. We want to get to this thing here. So just trust me in that this becomes this through partial fractions. Bit of a callback to integration techniques from term 2, where we learned how to do partial fractions, how to convert this one more complicated looking fraction into two simpler fractions. Okay, so that's what the left-hand side becomes. The right-hand side is still the integral of r on k dt. Now we integrate, and the integration here is pretty straightforward. The rule, I guess, is really just the integral of 1 on x dx is equal to ln of x. Okay, so that's the general rule that we're going to be using here. So if we look at this thing, oh, by the way, because we have 1 on k here, right, everywhere on the left, that cancels the 1 on k over here. Okay, so k, dividing by k bit has gone, so now we just focus on the integrations. Okay, so here the integral of 1 on n with respect to n will just be the natural log of n, absolute value. Over here, this will be the ln of k minus n, right? But we have to differentiate this thing here, and we get -1 from that, so that turns it into a minus. So that becomes a minus. Okay, and now over here, integrating this, that's just going to be RT and plus some constant of integration. Now we've integrated on both sides, so we should have really a constant of integration on both sides, And, you know, strictly speaking, we'd could say C1 plus C1 over here and plus C2 over here. But in the end, you're going to put them on one side together, and, you know, we could say that C is equal to, you know, the C1 from here plus the C2 over here. Okay, good. Now, this thing here, we can simplify this a little bit using some log laws. So we have, you know, here we go. The log of A minus the log of B can be thought of as the log of A over B. Okay, so that's another little rule. So we've got a couple of rules here. This is an integrating rule. This is now a log rule that we have to use. So we're going to say that's n over k minus n, and absolute value equals RT plus C. Good. Now, exponentiate both sides. So if we do that, we end up with n over k minus n equals e to the RT plus C. Now, at this point, it's probably important to note, and I should have written it over here, and I'll do it now, that our population at any time, which is n, it's always going to be less than k, and it's always going to be greater than the initial population. And I guess, you know, the initial population is always going to be greater than 0. So we know that n is always going to be positive, right? So it's never below the time or the x-axis here. It's always positive. So from this we can say that n is always positive, okay? And with that in mind, and because n is also less than k, if we come over here and look at this, what we have here on the left, we can see whatever values we choose for n, right? So here it's always going to be positive, here it's always going to be positive, and it's always going to be less than n, less than k. Because of that, we know that this will always be a positive. Okay, so we don't need the absolute value symbol surrounding that. We can just simply say it's that. And while we're at it, let's do the whole thing where we think of this e to the c as being some constant a, e to the RT, right? So because n is greater than 0 and n is less than k, we end up with this. Okay, so let's continue this. So what I'll do is I'll slide this over. Okay, so we can just still see that bit. So the next part will be to now algebraically manipulate this. Okay. What we could do, in fact, yeah, I'll just write it up here. So this is where we're at. We've got n over k minus n equals a e to the RT. All right, I'll keep going. So a bit of algebra. So n is, sorry. Remember, we're chasing this answer here, right? And you know this answer because it's given in the assignment. So we need n as a subject. Everything else on the other side. Looking at what we have here though, we've got an n here, we've got an n here. Now we somehow need to absorb these two n's into one n and have them the subject or isolated on this side of the equation. So I guess the first step is to maybe just cross multiply that over. So we've got a e to the RT brackets k minus n, okay? Then if we expand the brackets, we get a times k e to the RT minus a times n e to the RT, okay, equals n. Good, so the n we have here, the n we have here. We need to get them together on the same side. So let's move this across. So now we're looking at n plus, because that's a minus term here. This thing is a minus term here. So on the other side becomes a positive term. So we have n a, n e to the RT equals a k e to the RT. Now we're close because we have two terms here. N is part of both terms. If we factorize the n out, now we've absorbed the two n's into one, or we've created one n out of two, which is what we want to do, what we need to do. Okay, and just writing the rest of this out. Last step is, because we want to isolate n, is we're going to move this bit in the brackets across, which means we cross multiply it. So we're multiplying n by all of this. Over this side, we'll be dividing by that. So we end up with n equal to a k e to the rt divided by 1 plus a e to the rt. Okay, we're getting close. We're getting close. So let's just go back to what we were looking at here again. We're trying to get this answer here, right? Now it looks close, it's not quite there. A couple of things we can do. One is, if we look at this, whole fraction here, we can see we've got one term on the top and we've got the sum of two terms on the bottom. Now if we divide, and you'll notice that this term here has e to the rt associated with it. This term here has e to the rt. In fact, this has a e to the rt, this has a e to the rt. So these two terms have a common part. Now we can divide through. If we divide through by a e to the rt, right, then that will cancel. So let's do that. That will cancel a e to the rt on the top. So we're just left with k. It will also cancel all this term out, so that becomes a 1. Right, so we divide this whole term here by a e to the rt, we're left with k. We divide this term by a e to the rt. We have to do not just this term, but everything on the bottom, so we're dividing this term by that as well. So that's what happens. You could think of it this way. A e to the rt divided by a e to the rt, and then this was a e to the rt divided by a e to the rt. So essentially I'm dividing top and bottom by a e to the rt. They cancel, that doesn't. So we end up with this, n equals k over, right, and this is plus 1. Now this thing here, what can we do with this? Okay, we can say it's 1 over a, and then we can, using our index laws, we can raise e to the rt up to here and make it e to the negative rt. And then here's the last bit, really, where we say k over c e to the negative rt plus 1, where c is equal to the 1 on a. And you'll see that that's pretty much exactly what we needed over here. Okay, just the terms on the denominator are swapped around, but it's the same thing. Okay, I think I'll stop there. I'll stop there. There's more to do, obviously, because we need to come back and we need to show that C is actually this, and we get that through initial conditions. Okay, so using initial conditions, we can find that out. But I'm going to stop there for now. I'll pick this lesson up I'll pick this up in the next lesson, and we'll look at not only how we find the C value from initial conditions, but also how we can then apply this function, this logistic function, to some sort of real scenario. Okay, thank you.